Today I want to talk about a program called Qudi. Qudi is a platform made by the people in their own university to help people working on MB centers, and of course it can work with any type of environmental work that you are working, like any Confocal lab or any other lab. So anywhere that you want to get voltage, you want to send voltage, send commands with the cons, these kind of things, you can use this platform. So let's get it straight. So in order to have this platform, you need to install PyCharm, and you also need to get the file from the GitHub. So just to get from GitHub, if you're not familiar, is something very simple. You just need to go somewhere in the PC, then right click, get clone, and then just write the URL that is in the description, or the URL that is in the GitHub, or the GitHub that I will put as well. And then that's it. Just press OK. Once you press OK, you will see that, for example, here there will be a folder including the files that are synced and are not synced. Of course, they should be synced first, but we will see this folder, which we discuss about it later as well. Then you need to just, with PyCharm, you need to just open the project. You just need to go to the location where you get the Qudi. You just go to here. I have the Qudi on, and I just press open. And then I need to just open a file. I need to open the start file of the project, and then here it is. Yeah. Okay. Then I press OK. So then this is basically the start Py functions. And if I run it, I will get to this interface. So this interface, you have basically three sub interfaces. One is GUI, the other one is logic, and the final one is hardware. So in order to do something, you need to have a logic for that. And the idea is that for logics, then you will have hardware that they will do those logics. And what we see there, we see these logics in the graphical user interface. So for example, one graphical user is the counting interface, the other one is time series, and the other is Confocal, like doing a scan, piezo stage, and the one is ODMR, like just sweeping microwave frequency, do pulse measurement, and then kind of thing. So anything you can add here. You can even write your own files, your own graphical user interface, and you can even write your own logics, even your own hardwares, and just add them together. So just for test, we just run one of the graphical user interface. So it will show us this counter interface. If you see, it just had some logic. It initialized some logic, which is counter logic, save logic, also time series logic, which has been initialized for this one. So regarding the hardware, it needed also these NI cards for the hardware. So let's go to the counter. So what does it do? This is very simple. This is just simple the photon counter that we have right now. The laser is on, the counts are like this amount. If I just change the power of the laser, if we're using a cobalt laser, laser diode, this count will also change. So if I go further, then I have much more count, for 3 milliwatts. So I start for 2 milliwatts right now, for example, for this case. Then when we see, so here it is. So here you can just specify what is the count list that it wants to count for each cycle. So every 10 counts, it will show you the data. If you put like 500, so the more this is, the more accurate this count number will be, but the less it will take. It's like something like an average. Here, this is this bar. You can see. I will show you how to configure this one for yourself. And then there's the other part. I just briefly go to these parts so you know that if it is what it suits for you. So here you can also say what kind of port you want. You can say that what channels you want to have, analog channel or digital channel. So it's the same. It's like the upgraded version of the other part. And then you just press like start, and you see that we have like 100,000 times per second. So you can either see the average, or you can even see the actual counts. So moving average, this one is also can be seen. So here, as I said, you can introduce, add more channels to see the moving average, and then it works. So you see in the channel you have some voltage, this channel you have something, is this voltage in the other channel. So yeah, you see this is quite fast, quite convenient, easy to work. And then the last thing, the third thing is like confocal. So the confocal, which is nicely written actually. So you have this environment where you can just do some scans. You can just select some places, like for example, then press a scan, and then you can see, you can do some scans to see confocal map of what you have. So we here, I guess in this map, we have some pillars, pillar array. We want to do this. We want to see it. So if I put full range, so it's like, then we scan the full range. You should not be able to see in the full range probably because the resolution is not good here. So we can increase the resolution, and then you can see it. So even if I put 200, if I put 200 resolution for X and Y, and then just scan again, then I might be able to see something because we have like some PROR, very small. Let's see if we see something here. So what it's doing, it is moving the stage and seeing the photoluminescence, measuring it. It's just showing as a count. So it shows something, but not entirely sure if we are seeing the right array because they're too small for this big range. So you will see it's quite fast, quite convenient. Once this is done, you can save this value on your computer, and it will generate the PDF file, the text file, the data that it has, and every file that are needed for further processing in the future. It will also say that what was counts and everything. So probably we see some patterns here. Although you can see there's some patterns here. You can see there's some pattern. There are some patterns here. So yeah, for sure we are seeing the right things, but resolution is not good enough to precisely say talk about this pattern. So if you want to just zoom in, you just can zoom, and that's cool. So this software will understand a little bit less resolution to just maybe just to be faster, like maybe 50. See if we can already see some good pillars or not. Maybe I decrease the resolution a little bit. I also play a little bit with powder to see the pillars. So yeah, it might be the case that so it's just experimental. It might be the case that you are not in the good Z direction. So what you need to do, you just need to easily scan the depths. And for that, actually, there is something built in this software that you can easily do. This is Z scanning. So for that, you need to just press scan Z, and you need to just specify what range you want to scan. Then you will see here it will scan Z in one of these directions that you can choose from these options here. I think the Z is here. I think it is the right Z. I think there is some killers probably there. So I just moving this thing, I can instantly see, instantly put the position in the right place. Yeah, maybe the range is too big, but I'm pretty sure we should see something from 60 to 100, maybe. Let's go to 60 to 100 and like this like rectangle thing, and then restart the scan again to see if we are observing some pillars. I think we are seeing them. I'm sure that they are the pillar. Then let's do another zoom, like here, I think. Like here. You see? It's like really easy, really good to work. You see there are pillars here. Yeah, it was nice. We could observe the pillar easily. If you want to optimize on this thing, you can play around. You can even move up and down a little bit with Z and optimize on it, and that gets better, a little better of the scan, or just you see now it's getting better. So easily you see that you have these pillars, because probably we are focused on the side and on the surface. Then that's one reason that we don't see. We see that the pillars, they are less bright. So if you want to save this thing, you just need to only press this button, the save button here, file, save x, and if you want to press this like save like this, you can just press this. Then it will, I mean, depending where you use, you have already defined the software to save your data. You can just get the data depending on the date in the folder specified, and then here you can see the data for, you can see the data for the key, better data. Also in different format you will get it. You will get in different format. You will get also the raw data. You will get for different ports as well. So if you have multiple ports, you will just save all the data for all of the ports. And you have the PDF file, and if the file is generated here, you have also the text file, which you can see it's here. So yeah, that's it. And okay, in the last but not least, there is this ODMR. So with the ODMR, with microwave, you can just, for example, select the pillar. But easily you can just move this thing here and put the position of the piezo in the pillar. Then you select the power that you want to give, like the range, the steps, and you will run the ODMR. So what it will do, it will just try to see the microwave frequency here. You see, this adds them and average them. If you press this one to 10, it will just show the 10 average, the last 10 average. If you press to 0, it will show the average from the beginning. So you can see that you can already see some ODMRs, which seems to be quite nice. If you want to fit it, you can just write here fit functions, or you just can go here, just to define the fit that you want, or see the fit that is already here. So for the fit function, I press fit. Then you see it's already fitted something. I mean, it's not the best data. Maybe we need to just accumulate more. But we can already say something that there is something inside this data. 2.87, we use the zero field splitting of the MB centers. We can have like this, with like this, single as well. So if you want to save this one, you can also do like save, like just save like first test for YouTube, or just any dimension that you have here. You have the laser power, like laser, 1 milliwatt, anything that you want on pillar. Then you press this, and it's saved. It is already saved now. So if you go to the right direction, we can say that it is like here. If you go see, there is an ODMR folder here, and this is for different different input. It's loaded by this or this, but this is what we got. Data is also here. So you see it's getting better and better. No, of course that is starting, but it should be better if you just continue. This is just the runtime of the measurement, the start frequency step, and the power of the microwave. Here I have a microwave amplifier on the way, like 48 dBm microwave amplifier, so I put minus 10 dBm is good enough to see something. So you see there is different ports. For sure you should not be able to see anything with different ports. There's some oscillations because nothing is connected to them. Okay. So that's it. So we save this thing. Let's see. Okay, then if you want to just do some pulse measurement in a pillar, then you will go here. Then you will have this pulse. You will have pulse sequence that you are interested in. For example, if you want to do T1, you just need to give the value for the T1 that you want to measure. Like for example, start from 1 microsecond, which is step of anything that you are interested. For example, if you want to do T1 for 1 millisecond, you should do like 100 microsecond with the step and like 10 points, but let's do what 50 milliseconds, for example. Then how you grade these things, you also bring this in predefined methods. You just bring T1 and just apply it, and then T1 is there. And you press, if you press alternating, then it is 2 pulses would be the same. So for example, the pulse at top equal to 100 microsecond will be repeated 2 times. Like periodically, then it's more accurate. But let's do normal. You just select what is your microwave channel. You need to select what is your laser channel that your pulse generator goes, and also your sync channel. You need to also specify what is the resolution that you are going to require, what resolution you are going to require. If you are using the external microwave frequency or Rabi, you need to say frequency and the microwave power. That's it. Or you can also define the pulse that you like to make here in this pulse simulation. If you want, for example, to make a pass to channel 1 for 10 nanoseconds, then channel 2 for 20 nanoseconds be on, and then nothing in between, then channel 3 for, then you can just define it, what is these channels, and then you can say, and you just need a name, like test YouTube test video, and then generate pass. You see test video is here. You need to then go here, the passbook, find your test video, number of repeats, how many repeats you want to do. 4 repeats, of course, here because it makes sense, but because this is only this one. But if you want to add something else, like another sequence that we made, like with the way that we made before, you can just change this one, and then after finding a name like ensemble test lead, then you can generate the pass. It will tell you that how long it will take this pass sequence. So this is a good number in order to know that what will be your counter equivalence here. Then you just generate and sample and load. So this will be sampled and load to your pass generator. See, so you could just generate this sequence in the pass generator. You can also make sequence generation, like events, time, trigger, wait for, like a bit more complicated, but here, yeah, I think is good enough in me to make that. But here we want to do T1. Let's do the T1. We just make 1 microsecond, 100 microsecond, 50 number of points, and here we say that what is the beginning of the pulse. So for example, the first 2 microseconds of the pulse, start from the first 2 microseconds of the pulse, and for 10 microseconds, so it goes from 2 microseconds to like 12 microseconds, and here is 48 microseconds, like in the middle of the pulse to the end of the pulse, to just measure as a reference. So how it does, it just either take the mean of the first analysis window and the mean of the reference window, and then it just shows that analysis window means that reference system, or it just take the mean of analysis and then mean of the reference, and then take the normalization by the analysis the reference, and or you just subtract them here, and here you just calculate the sum and also pass through function. Like this is the analysis method that you need to. And here is like how to find the pulses. So here in this method, we just calculate the convolution of the pulse with the Gaussian function with a standard derivative of 5, and then once it is smoothened, then it takes the first derivative, so it finds the Ising value, and it finds the pulse. So yeah, so we press these things, and we selected here the record length. This is the resolution. This is the beamwidth, basically the resolution that you will have in the pulses. But this is the beamwidth you will have, is best to say. And here is like the label here. Label. What was the label? You can just invoke the setting from that part. You know, the way that it's now modified is that you need to put the country coordinates I, so you can work with the ML card. It's very nice. That you work with the ML card. You can just, once you run this thing, you can just get the result for your pulse measurement. Yeah, right now the laser, I need to also put it in modulation mode, which we can do in the separate another tutorial where I will really dig into all of these things, and I will do one T1 measurement and show you how it works. So I hope you like the video, and I hope it will be helpful for you. If you have any questions, write in the comments, and don't forget to subscribe. Have a good day, and I wish you that you can just do everything very good yourself.